Hi everybody and welcome back to the new series of videos on logarithmic functions. So before we talk about the logarithmic functions, we are first going to talk about this exponential function onto the x. So let's graph it first thing. So we'll draw a line here for the x-axis. And we'll draw a line here for the y-axis. And so I'm going to let these units be 1. And so let's draw this graph. So we're going to always go through this point 0, 1. We'll go through the point 1, 2. At 2 we will be here, let's see, 3, 4. At 2, 4. At 1, negative 1 will be at a half. And then at 2, negative 2 will be at a quarter. So this gives me a nice, good graph I can draw. For this exponential function with base 2. Now, remember that we said that this function is one-to-one. And so one-to-one functions have an inverse. And this inverse that this function has is not a type of function we have seen before. So let's look at the graph of it first. Sorry about that pop-up. I should have closed my email. So let's draw the line y equals x at here. So here's y equals x. Remember that the graph is supposed to be reflected about this line y equals x. But what does that really mean? Well, think about it in terms of coordinates. That means that that just the x and y coordinates switch positions. So instead of having 0, 1, we'll have the point 1, 0. Instead of having the point 1, 2, we'll have the point 2, 1. Instead of having the point 2, 4, we will have the point 4, 2. And similarly over here, we'll have the point that is negative 1 1/2. So we will get a half, negative 1. And then over here we will have negative 2, or negative 2 a quarter. And over here we'll have a quarter, negative 2. And notice that we just get this reflection through the line y equals x of this graph here. And notice other things reflected. For example, the original function 2 to the x had a horizontal asymptote here. So notice that our new function we constructed, the inverse, has a vertical asymptote. So notice the horizontal asymptote, when it gets reflected, became the vertical asymptote on the y-axis. And then all the coordinates obviously switch places. So this function that we've graphed here, this is known as the logarithm base 2. Because the base here refers back to the original exponential function that has base 2 here. And that has a notation. This is going to be the function f of x equals log with a subscript of 2x. So notice that one thing I want to talk about notation here before I actually give definitions is this log x is just another way of saying f. So these, in fact, are the same notation. This is really log base 2 of x. Or you can even just write it like this, where we're just replacing the f with the log base 2. So one of the things about this notation that people really mess up is the fact that they just write log base 2. Well, no, you're just writing the name of the function. It needs to have some expression to evaluate it at, and so our generic first example is always just x. So let's move on to the definition. So let's zoom in just a little bit. So definition. So again, b cannot be negative and cannot be 1. And so The inverse of the exponential function is called the logarithmic function with base b, where the base b again refers back to the base of the original exponent that it was derived from. It is denoted as log base b of x. And the only reason I'm using the f inverse notation here is because I've already used f here. Usually we'll just write f or g or whatever. So notice that properties here, so I'll zoom in on properties a little bit. The domain is 0, 0, and that's because and this is all for logarithm, so this is log base b of x. But notice that for b to the x, the range was 0 to infinity. And remember that the range of the inverse function has to match the domain of the original function, so these match. The domain, or the range of the logarithmic function are all real numbers. Well, that was the domain of the exponential function. So again, notice that these things match. Passes through the point 0, 1, and that's because we always pass through the point 1, 0. And so to reflect across this line, all we have to do is switch the coordinates. Has a vertical asymptote y equals 0. I already talked about that. That's the x, the horizontal asymptote getting reflected through the line y equals x, so it becomes now a vertical asymptote. Always increasing if b is equal to 0. Well, that makes kind of sense, so let's look at this case real fast. So if b is greater than 0, the exponential function looks like this, so the logarithmic function will look like that. But so this is b greater than 0. But if b is less or between 0 and 1, notice that the graph of the exponential function looks like this. And so the graph of the logarithmic function is going to look like this instead. Oh, no, that's a crappy graph. It will look like that instead. So always decreasing if between 0 and 1, always increasing if b is greater than 0, and then because the exponential function is 1 to 1, so is the logarithmic function, otherwise they won't be inverses. So those are the basic properties of logarithms you should know. We'll talk more about additional properties in future videos, one for this set and then one for the set on Monday. Up next, we're going to talk about calculating between exponential and logarithmic notation. See you then.